Okay, what do I mean by bandwidth limited? Well, basically I need a definition of bandwidth. So I'm not going to get too far into this. You should have already be familiar with this from signals and systems. But we're going to say bandwidth is equal to twice the minimum of the set F, so that if I take the Fourier transform of a signal, so let's say I have a signal S of t, and the Fourier transform of that signal S of f. So if I take all frequencies, the set F of all frequencies, and I take the minimum frequency so that the magnitude of the Fourier transform is less than or equal to some small epsilon for all f prime greater than f, and I'm going to call that the bandwidth. So what does that mean? Basically this, if I have a signal that does this, and epsilon is down here, then f is the minimum so that everywhere beyond here, the magnitude of the Fourier transform is less than epsilon. In other words, there's just some threshold beyond which I call epsilon basically the Fourier transform component that I don't care about anymore. So the bandwidth is twice this frequency. Bandwidth goes from minus f to f, and that's because signals are, real valued signals are symmetric in the Fourier transform. Okay, this is possibly more complicated than you would think it has to be. You might think bandwidth is the set of, is the sort of collection of frequencies where the Fourier transform is non-zero. Does anybody know why that's not a good idea? Did you ever cover in signals and systems that if a signal is limited in time, that it's actually infinite in frequency? No? Okay, it's true. So you have a signal like this, basically, that goes from 0 to TB in particular, for some bit time TB. And you take the Fourier transform of that, any such signal that's limited between, let's say, 0 TB and 0 everywhere else, there is no maximum frequency for the Fourier transform. So that's why we have to sort of go to this trouble of defining some epsilon beyond which I don't care anymore, because usually they will roll off. Usually these Fourier transforms roll off, and there's some point at which it becomes negligible, but it never becomes 0. So this is, I won't say much more about bandwidth than that, except to say that bandwidth is usually proportional to 1 over the bit time. And that makes sense. So bit time, which is equal to NB times the sampling time, that's basically the fastest rate at which the signal changes. So usually you would expect that if the signal is changing every TB, then the bandwidth should have something to do with TB. So under most reasonable definitions of bandwidth, for most reasonable values of epsilon, the bandwidth will be proportional to 1 over TB. In fact, for the purposes of this class, let's go so far as to say that B is equal to 2 over TB. I've seen that in some books. So if I ever say the bandwidth is something, this is what we're going to do. This is what we're going to say. Okay, remember that when I sample, I have to satisfy the Nyquist sampling criterion. So it's worth remembering that the bandwidth over 2, which is the sort of the one-sided baseband bandwidth, has to be greater than or equal to 2 over Ts. Excuse me, less than or equal to 2 over Ts. That's the Nyquist sampling criterion. In practice, for ease of signal processing, we pick Ts so that Ts small enough so that this is much bigger than that. Okay, so that's the first requirement. I need this band limited signal so that when I shift it in frequency domain up to here, it's still limited in bandwidth so that this bandwidth doesn't exceed the criterion that I need. The second thing that I need, remember I said, is I need to be able to shift this. I need some mechanism by which this gets shifted up to here. Anyone suggest one? Do you remember this from signals and systems? Is that? No. Anybody remember this? Really? Nobody? No? Okay. Nothing? Is this thing on? No? Okay. You multiply by a sinusoid. Oh, okay. So we have, this is S of t. This is the Fourier transform of S of t. And this, if that is f, some frequency fc, this is S of t times cos 2 pi fct. Actually, we also have the image down around minus fc, but I'm going to forget about negative frequencies because they don't really matter for our purposes. Okay, S of t times cos 2 pi fct is how I get this. Does anybody remember how I get it back? I can't multiply by cos minus 2 pi fct. What can I do? This is where the negative frequencies come in, but I don't care about this. I'm just wondering if anybody remembers. You could do that, except this is 0 sometimes, so that's what you do is you actually multiply again by cos 2 pi fct, and you get S of t times cos squared 2 pi fct. Cos squared 2 pi fct is actually equal to 1/2 plus 1/2 cos 4 pi fct. So you have S of t plus S of t times some cosine at twice the frequency. So you get your original Fourier transform centered around 0, and some Fourier transform centered around 2fc, and then you blow past filters like that. So is this ringing any bells at all? No? Okay, I don't care. Yeah, so you should have learned that in signals and systems, but it doesn't really matter as far as I'm concerned. This is the important bit, is we multiply by the sinusoid. Okay, so basically what we do is we form S prime of t is our original signal times cos 2 pi fct. Okay, I don't, there's quite a bit to talk about here, and I don't really want to start getting into it, but what I will show you is the following. So the same arguments apply if I have a cosine with any phase shift, so I could have S prime of t equals S of t cos 2 pi fct plus theta.